Okay, so we need to start here. I couldn't remember, oh my gosh, Wednesday seems like forever ago. And it was. So what I did was actually looked at the video that I made to find where the last slide we did. Okay.
So wait, did we do page 44?
I think so. I think we did this one, right?
Maybe I think we skipped ahead a little bit, went back. That was like a different day.
Could be, but this is the next slide after the building slide. Yeah, I think we did. So you guys told me Newton's second law is force is equal to mass times acceleration. Newton's first law is the whole thing where an object, whatever motion it has, is going to keep that motion unless some other force acts upon it, okay? And that actually includes an object that's at rest. So an object at rest will stay at rest unless some outside force works on it. And that's where, I could put my pen here and I could put a sheet of paper underneath it, and that pen has a certain amount of what we call inertia, okay? Just at rest, it has a certain amount of inertia. So I could pull something out from underneath it and the pen's supposed to stay there, okay? Kind of related to this is this concept of momentum. So inertia has to do with mass of the pen. Hey, if I had like an elephant sitting there, right, and I tried to pull a paper out from underneath the elephant would really stay there, okay? It has more inertia. The elephant actually, if the elephant was moving, has more momentum. Momentum is like, if you get home at the end of the day and you're like, oh, I got to keep moving or I'm going to lose my momentum, okay? Basically, you're saying I have to keep going because I have a certain amount of momentum to get things done. When I stop, I'm going to stay stopped. That's actually Newton's first law. But momentum has to do with the mass of the object that is moving. So momentum can actually be calculated by multiplying the mass times the velocity. Momentum is mass times velocity. And remember, velocity is both speed and direction. So it's what we call a vector. Okay, velocity is a vector. So momentum is also a vector. Okay. So the example would be like if you have, what momentum does a bicycle have driving down the road at 35 miles an hour versus a Mack truck driving down the road at 35 miles an hour? They both have the same velocity, okay, but they have different masses. Okay, so that means that the truck has a lot more momentum than the bicycle does. Okay, so momentum is kind of related to inertia, I think. So if something, what we're going to see here in a minute is that momentum needs to be conserved. So an object has a certain mass going a certain velocity. It can interact with other objects, but that momentum that it has is a type of energy that needs to be conserved. It can't be just once they have it, it can't go away. Momentum needs to be conserved. Momentum can be changed, though. If an object changes its momentum, that means that some force has been applied to it. It's kind of like Newton's first law. Okay, if something changes its velocity, okay, it changes its momentum, and the only way it can do that is if some force has been applied. These other couple of thoughts on the slide are somewhat not related directly to momentum. But here's a thought for you. This happens a lot. Okay, forces, we think of a force as kind of a push. But oftentimes, on a given object, there's more than one force working on it. So like this force, or this pen, if I go like that, okay, there's a number of forces. I forced it that way. It eventually stopped, probably because in a little bit friction, force of friction, and there's the force of gravity pulling down. So life is complicated, right? So we can have multiple forces acting together, and you can add them together. Forces are vectors too. We can use little arrows to actually size and direction of the force and add them together to get the net force. So on Wednesday, we did the whole slide with the guy dropping something off of a building, and it went faster and faster and faster, which means it was changing its velocity, and things can't change their velocity unless a force is acting upon them. Okay, so acceleration, change in velocity. Okay, you have to have a force working on it. which actually gets it back around to Newton's second law. Force is equal to mass times acceleration, so we kind of come full circle, okay? If something is changing its velocity, it's accelerating. If it's accelerating, there must be some force working on it. So a lot of times, we shouldn't, but a lot of times we'll kind of use the terms mass and weight interchangeably, but we really shouldn't. Okay? Mass, by definition, is the amount of stuff an object contains. Okay? So it's kind of looking at basically the atoms. Okay? Mass is kind of the atoms kind of an object has. But weight is, you probably think of weight, I'm going to step on the scales in the morning. Okay, weight, on the other hand, is an object has mass, and the force of gravity works on that mass to create another force called weight. Okay, so actually weight is a force. Weight is an interaction, a gravitational interaction. So if we want to calculate weight, and again, we're not going to do any, I'm not going to have you do any calculations in this class, but W, weight, all we'd have to do is take the mass of the object in kilograms times G is the acceleration due to gravity. So on Wednesday, we learned, in that slide anyway, we went with a value of 10. Okay, so this is, M is the mass, and G is the acceleration due to gravity, which is 10 meters per second. For every second something falls. So it's 10 meters per second actually squared. So there you go. That's the weight. So put another way, the mass, the atoms, the amount of matter that something contains, okay, is constant. Whether you're here, whether you're in outer space, regardless of any sort of gravitational thing going on. So mass is constant, but weight will vary. The example to look at here is if you were on Earth, you would step on a scale, and your scale would read something. Okay. Then if you had the opportunity to travel to the moon, take your scale with you, put the scale on the moon, okay, weigh yourself again. Actually, you might be happy with the results. You'd be like 1/6 the weight. Maybe you wouldn't, I would. Okay? And the reason our weight changes on the moon is because the force of gravity changes. That little formula up there, W is equal to M times G. The G on the moon is about 1/6 as the G on the Earth. Okay, so your weight would change, but your mass would be the same. So speaking of weight, okay, here we have A, B, C, and D, 4 scenarios of a guy, for whatever reason, trying to weigh himself on the elevator. Okay, you're like, really? Oh my goodness. Okay, so he's got his scale here. This scale here is hard to read, so actually, if you look up at the top there, that's what the scale is reading. So here we have basically the scenario A is that the elevator isn't stopped. The elevator is not stopped, but it's going at constant velocity. So it's not accelerating. In that case, actually, even if it's moving, if it's not going any faster, it's the scale is going to read the same as it would normally, yeah. So you can see he weighs about 140. So in scenario B, it's actually accelerating upward, okay? And you can almost feel if that's accelerating upward, I bet my scale is gonna, I bet I'm making more of a force on my scale. And actually that is the case, okay? You can see it jiggles a little bit, but his weight increases. His mass stays the same, but he's got acceleration also going on. In this case, he is actually accelerating downward, okay? I know you guys have felt this when you've gotten on an elevator before. You know, it's that first bit where it gets to a constant velocity that you're going, whoa, and then a constant velocity, and you're like, okay, that's fine. Okay. So actually, in this case, his weight is a little bit less. And the last scenario, and we're going to be talking about this on the next slide, the last scenario is very bad. the cable breaks, and the dude falls, right? And so basically, the way I think of it is not good. Okay, his scale falls. Okay, his scale falls and he falls. So really, you can kind of see what the scale's reading is basically nothing. There's no force on the scale. Okay, he's in what we call free fall. So this is kind of a neat thought. If you've ever watched, like, the International Space Station, the ISS, is great about taking their astronauts and doing a little bit of PR, so they make little videos of their astronauts in outer space. The astronauts kind of floating around. So, but those astronauts in the ISS, the International Space Station, they actually are being influenced by gravity. They are being influenced by gravity. If they weren't, they wouldn't be orbiting the Earth. So here's kind of what this looks like. Here we have a few scenarios. This is kind of silly. Have you ever heard about this, like, elevator to go up into outer space? This is what this reminds me of. Okay, it's basically the guy is going to climb something tall, okay, and we'll call this A, B, and scenario C. Scenario A, basically, he climbs something very tall and he just steps off. Like, oh, dude, splat, right? I hope he has something down here to catch him. Okay. Scenario B is he walks off, but he's going a little bit faster. Okay. Notice if he's going a little bit faster, where does he land? He lands a little bit farther on Earth. Okay. He basically, the way I think of it, he has a little bit of trajectory going this way, so he's going to fall farther on Earth. Earth is round. If the Earth weren't curved, he wouldn't do that, right? Well, he would, but scenario C, he gets smart, and somebody in my other class said, can they do that? And I don't think so. He gets smart, climbs something tall, and puts something on his back that's going to give him a boost in that direction. Okay, so he gets a boost in that direction. Gravity still pulls him downward, but instead of intersecting with the Earth, he basically falls into an orbital pattern. Okay, so here he goes. This is the last scenario. Okay, in this scenario, he's going this direction. He's being pulled this direction by gravity. Okay, his resultant is right here. Okay, and actually anywhere along that, if you take him right here, okay, again, gravity is pulling him down. Gravity's pulling the ISS down. Okay, it has a boost in this direction. Okay, and the resultant is, I'll choose red. Okay, is that. Okay, so they are falling to the Earth. It's just that they're missing the Earth as they fall. Okay, so it's free fall. Free for all fall. Okay, so it feels like there's no gravity, but there's definitely gravity working on them. All sorts of logistics of astronauts. Maybe you've kind of followed some of these, like, you know, how do you go to the bathroom? Or how do you eat? How do you put out a fire? You know, things are weird up there. I'll have to see if I can find some little videos. So, I mentioned momentum needs to be conserved. One of the things about science or physical science is we track quantities, like we do number crunching and we look at quantities. And we are counting on a bunch of things being conserved. Okay, it's an ongoing theme. So for instance, we count on matter. Like once there's matter, it's always there. It can't just poof, go away. Once there's energy, energy can be converted between different forms, and we'll talk about different forms of energy. But you just can't have energy one minute and the next minute don't have energy. It has to be conserved, and in science we count on tracking those quantities. The other thing about science is that we track those quantities down here on Earth, okay, and we actually also track those quantities in the cosmos. So it's kind of neat how earthly stuff is applied to, like, said the cosmos. Momentum is conserved. In a minute, I'm going to talk about what's angular momentum versus regular momentum. But I did want to mention this, okay? Actually, I say once you have matter, you can't, that matter, poof, can't go away. And once you have energy, you can't destroy energy. Sometimes it looks like it goes away, but it really is somewhere. But there is this relationship, and it exemplifies itself in nuclear reactions. Of course, you're probably familiar with Einstein's equation linking energy, E, and matter, M, or mass. So that's energy. And I think we talked about this earlier. So you can make those go back and forth. So the theory of conservation. It's not a theory, excuse me, the concept of conservation. So quantities can be transformed, especially energy is great at this. You can get different types of energy, but it's always you can track where it went.
What does the C stand for?
The speed of light. I think it's 186,000 miles per second.
Oh wait, can you go back to like the one second? Oh, okay.
Get it? Okay, so regular momentum was the whole the whole bike and Mack truck going down the road. Regular momentum, all you got to do is take the mass of the object and multiply it by its velocity. That's regular momentum. Angular momentum is associated with objects like planets that have some sort of twisting. And actually, it could be angular momentum is associated with rotation, and angular momentum is also associated with orbit or revolution. Okay? So angular momentum has, you see that the M term is the mass, the V term is the velocity, but now we introduce an R term. So angular momentum. So the R term could be a number of things. Like, for instance, the R term for a rotating, spinning planet, if we're looking down at the pole of the planet, okay, and it's spinning on its axis, actually this value would be R. Oops, lowercase r. This value would be R, from the outside of the planet to the core of the planet, if it's rotating this way. But in the case of a planet orbiting, okay, we have a different R. So this actually is, well, it's Kepler's maybe first law, okay, kind of showing the shape of the orbit of a planet about the sun. You guys would tell me that's an ellipse, okay? The other thing we know about what Kepler came up with is that the sun is off-centered. It's at one focus of the ellipse. So actually, since it's off-centered, we kind of have what we call perihelion. See, some of those terms we talked about before, we're going to talk about again. So that's, I'll point to this position. I'll call that perihelion. Okay, and this position is aphelion. Okay. So if angular momentum exists, and if it's conserved here, I usually kind of learned the symbol for angular momentum is P. So P, angular momentum, is equal to mass times velocity times the radius. So here's the deal. Can you see where this radius here, when it's at perihelion, is small? So radius at perihelion is small. So the momentum is conserved. So can you see what happens then is if this is smaller, if this goes down, the velocity needs to go up because the mass isn't changing. So So at perihelion, the velocity, my R's and V's look like, sorry, the velocity increases because of conservation of momentum. One goes down, radius goes down, velocity goes up. This actually is Kepler's second law. You know, we said basically at perihelion it goes faster and at aphelion it goes slower. We could kind of think through it the other way too, where the momentum over here, okay, it's got to be the same as the momentum over here. Okay, so P is constant. Of course, mass is constant. Okay, here actually then we have the radius is increased. And since the radius increased, that means that the velocity must decrease. And actually that's what it does. So velocity decreases. It's a little math game, but it's like the real deal, which is kind of fun. So that's orbit. Now we have an example up here of spinning. It's not a planet, but it's a person. So think of a skater who starts spinning. I don't know how she does it. I gotta do it. Okay. But starts spinning with her arms out. Okay, so the fact that she's spinning means that she has angular momentum. And picture then her taking her arms and moving them in. Okay, she spins faster. Probably seen that before on TV. Or maybe done that before, I don't know. So basically, again, she is decreasing her radius. Okay, so as you decrease the radius and pulling her arms in, you need to increase the velocity. And angular momentum is, again, conserved. All right. So I said energy needs to be conserved, but it can kind of go back and forth. Units of energy, in case you're wondering, are in the metric system, they're joules. In the English system, they're calories. Okay, tracking that energy, give it a unit. So we're going to spend a little bit of time talking about potential energy and kinetic energy. If you want to, on this slide, go ahead where it says stored or potential energy. I'm going to call that PE, potential energy. And guess what? Kinetic energy is going to be KE. So these kind of go together, I think. Okay? And we'll talk about them here in a minute. But kinetic energy is always energy associated with motion. Then kind of I have sort of just a miscellaneous kind of type of energy. One type of energy is radiation. Okay? And an example of, for instance, something radiating would be the sun. We're going to talk a lot about different types of families or little groups, subgroups of radiation coming from the sun, subgroups of energy. But the energy from the sun is what we call radiation. Then think of like this beautiful plant down here. It actually does chemistry, chemical reactions to convert that radiation to something that it needs. Okay, so there's a conversion taking place. The car, right? Again, with the chemical reaction, what your car does is to take fossil fuels, things that were in the ground like, billions of years, fossil fuels, to burn them, a chemical reaction then ultimately leads to your car moving. Okay, and associated with motion, of course, is kinetic energy. Kinetic energy is associated with motion. So those bikers up there, they consumed food. Food, as it is just sitting on the shelf, is actually potential energy. Okay, they consume it. Okay, and their bodies convert it to energy that they can use to motate on their bike. So focusing on KE, kinetic energy. Kinetic energy is associated with motion. Now, in order for this to kind of make sense, I need to make you aware, maybe you weren't aware, but all atoms, all stuff actually is in motion. It doesn't look like this table is moving, but it is. All the molecules are moving. All matter has motion. Okay? All matter has motion. So if it has motion, all matter has a certain amount of kinetic energy. So let's kind of look at two chunks of matter in these boxes. Okay, we have box A on the left and box B on the right. So right away, can you see, just if you're a visual person, can you see box B, that the arrows in box B showing the motion of those particles, that those arrows are longer. They are going faster. Okay, right away I can actually tell you that if these are the same substances, the fact that they're going faster actually is related to, if we could put a thermometer in box B, it would read a higher temperature. These things are hanging out at a higher temperature. That's how that works. Okay, so cooler temperature, higher temperature. Sometimes we get the whole temperature and thermal energy mixed up. Okay, temperature and thermal energy are not the same thing. I'm going to kind of show you why here in a minute. Right now. So temperature and thermal energy are not the same thing. So here we have a couple of other scenarios. We can call this pot of boiling water scenario A, and the oven with water vapor scenario B. Okay, so this is A, and this is B. So if we just kind of look at the arrows, of course the arrows over here look longer, and indeed it is at a higher temperature, 400 Fahrenheit, so that's actually water gas, H2O gas, floating around in there. Okay, the water molecules over here actually are just at the boiling point temperature, so this is H2O liquid. Okay, just kind of, but they're going slower, right? Slower, as indicated by the lower temperature. It's going faster. Okay, but do you see where, if the numbers are right, do you see where these have fewer molecules? You know, if it's drawn to scale, fewer molecules. So actually, that's why this slide says, even though they're ramming around there at our temperature probe would say 400 degrees Celsius, the fact that there are fewer of them, collectively that chunk of water gas has less thermal energy than that pot of liquid water, even though it's a higher temperature, lower temperature. This has more thermal energy because there's more mass there, there's more matter there. And you could do the numbers to crunch and convince ourselves. This actually, I know your textbook says that this is a more dense situation. Does this look, I don't know if you're familiar with the concept of density, but density is basically how packed stuff is together. So actually, this is more dense, and this is what we say more sparse. Okay, less dense, more dense. Okay, so actually, in order to say what thermal energy an object has, you have to consider both its temperature and its density. So temperatures. Okay, you're probably familiar with the Fahrenheit scale a little bit, like you know when it's hot and when it's cold, with regard to Fahrenheit. So Fahrenheit is the English scale, Celsius is the metric scale. But I also need to kind of go through, in case you haven't heard of the Kelvin scale before. So K stands for Kelvin. So the Kelvin scale, go ahead and put this whole thing up here so you can fill in the blanks. Oops, go back. So the Kelvin scale is also a metric scale. So English for Fahrenheit, metric for Celsius. And the thing that about metric was they kind of got something right. They said, all right, well, if water is so important, okay, water freezes at 0 Celsius. I don't know. Okay, water boils at 100 degrees Celsius. That's cool. But then the metric, also metric system, the Kelvin scale came out. I think that was probably the order. The thing about the metric system is basically it is offset. The 1 unit of degrees Celsius is equal to 1 unit on the Kelvin scale. There's like They're like lock and step together, which is pretty cool. So that means actually the Kelvin scale is just offset from the Celsius scale by actually 273.15. Now, the reason they came up with the Kelvin scale so we could do physical science problems was on the Kelvin scale, it's fancier because the Kelvin scale for the 0 Kelvin actually has an important, is significant. 0 Celsius, not so much, who cares? 0 Kelvin, we do care. Okay, 0 Kelvin is what we call absolute zero. The thing about it is that as you cool something down, it goes, okay, all matter has motion. If it doesn't have motion, it's not matter, right? It has to. Okay, so all matter has motion. As you cool it down, it goes slower and slower. Okay, so you can cool down to 0 Kelvin and it stopped moving, which it just violated a law of the universe, that sort of thing. Okay, so absolute zero. I will tell you one of the things this summer that really bothered me, I don't think I told you the story yet, but we went to the Adler Planetarium, which is a great planetarium, and they have a lot of neat exhibits, and they have the things with the planets, you know, each planet has its own little plaque, you know, each little kind of little module thing. And all of the planets, they gave the temperature, the surface temperature of the planet, which I'm like, cool, that's neat to know. But what they did was they had like a scale, and they said the planet's surface temperature is here. And its scale, no kidding, actually its scale went down to, I think it was negative 300 degrees Celsius. That was the scale that we saw for each of the planets. Because I started with Pluto, I'm like, really? Okay. Now, there's nothing that cold, and of course no planet's got, surface temperature's got that cold. But my point is, there's no such thing as negative 300 degrees Celsius. It just drives me nuts. Okay, the coldest anything can ever be is negative 273.15 degrees Celsius. So boo on them. I'm thinking about contacting Neil deGrasse Tyson and sicking him on him, so we'll see. It's on my list of things to do. I got pictures. And then I wonder, like, did they change it? Like, if I went back now, did they change it? I doubt it. It's like all the planets. So potential energy and kinetic energy. Potential energy is stored energy. Kinetic energy is energy associated with motion. Now, there's different types of stored energy. Like we said, a hamburger is stored energy, right? Now, there's also stored energy relative to gravity. So, for instance, this sort of potential energy associated with gravity sometimes is called potential energy due to its position. So, for instance, if I put my pen here, it has this far to fall. Okay, we can let gravity do its thing. Because it can fall this far, this is kind of how much potential energy it has. Okay, I can do that. Okay, now, oh my gosh, it really can't fall at all. So it has zero potential energy. That's kind of how that goes. So here we have a ball being thrown up in the air. Okay. So if we kind of think of the whole, it's thrown up, and I want to start right there. Okay, it's thrown up in the air. It stopped moving up. Okay, it's kind of hovered. Well, it doesn't hover. Okay, but now it's ready to fall back down. Up there, when it's at the top, it has actually the most amount of potential energy it's going to have in that little throwing period. So here we have maximum potential energy, max PE. I'm going to say velocity is equal to 0. Oops. Velocity is equal to 0. Okay, so actually KE is 0. Well, I know it's moving on the, like the little atoms within the ball are moving, right? So it does have kinetic energy, but we're talking about it's the whole ball. So then actually right before it splats on the surface, okay, it basically has, I'm going to say minimum amount of PE, potential energy, because it doesn't have much to fall. Okay, but it's going its fastest. We talked about how acceleration due to gravity. So since it's going its fastest, that means it has maximum kinetic energy. Okay, so actually potential energy was converted to kinetic energy. Well, in astronomy, especially like in, let's see, this is chapter 4. In chapter 6, when we talk about the formation of our solar system, this is actually a player. Again, it's a type of potential energy, but it looks like this. Can you kind of see scenario A and scenario B? Okay, scenario A is basically a cloud, and actually we're going to see that our sun formed from a big old nebula, humongous nebula, right? And when something is large like that, it has a lot of what we call gravitational potential energy, okay? So a lot of gravitational potential energy. And when it gets smaller, it begins collapsing, which we're thinking it got stimulated somehow. Then actually when it's smaller, it has less gravitational potential energy. It needs to be converted to something, and the thing it's converted to actually is thermal energy, or heat. Okay? So this is what our solar system started out with. Okay? It has lots of PE, lots of potential energy. Okay? And when it got smaller, it has significantly less PE, and now it has more KE, more kinetic energy. And I'm going to go ahead and put under kinetic energy, I'm going to say thermal energy. So, because the thing about it, in order for stars like the sun actually to shine, they have to have really hot cores in order for nuclear fusion to happen. And that's a player in this conversion of gravitational potential energy to kinetic energy. Oops, sorry. I guess I didn't do it. Did you guys need that one? Okay. So we're going to kind of revisit this this idea when we talk about other things in astronomy. So I thought we did this slide when I said E is equal to mc squared, but here it is. Converting matter into energy. So Einstein said it could be done, and it's really kind of cool. Basically, what's happening in the cores of stars is it's usually hydrogen, or actually our star is taking a couple of atoms of hydrogen and fusing them together and making helium. Okay? Here's the deal. If you weigh these two hydrogen atoms versus the helium that's formed, you're going to find that the helium, it's less matter. It's less mass. There's less mass. There's mass that's lost. Okay, and it's that mass that actually then is converted into energy according to E is equal to mc squared. So C is a really big number. It's 300,000 kilometers per second. Okay, so just a little bit of matter gives you a lot of energy. Okay. So Newton had 3 laws of motion. Newton also, and he invented calculus? No. I think somebody else, at the same time did it. But anyway, so he also came up with mathematical relationship for that force of gravity that we've been talking about. Okay? Here finally is the force of gravity that we've been alluding to. Why do we stand on the Earth? Okay, it's because our mass is actually interacting with Earth's mass. It gives us weight. Okay, force of gravity gives us weight. So mathematically speaking, it looks like this. The force of gravity is equal to capital G, which that's a constant. There's a lot of constants in the universe. That's just like something you would look up in the table. And also then in the numerator is the mass of the two objects multiplied by each other. So here we have a green object and a gold object, both with masses. Okay. Notice that as we increase either one of the masses, what happens to the force of gravity increases too. Then the force of gravity then, in order to calculate it, you have to divide by the distance between the two objects and then raise it to the second power, distance squared. So it makes sense that actually the more the distance between the objects, okay, you're increasing that term in the bottom, so the force of gravity actually decreases. kind of the makes sense sort of law. Okay, so the force increases with increasing mass and decreases with increasing distance, and it kind of makes sense. So the force of gravity is, we definitely see here on Earth, and we see in outer space all the time. All right. So do you remember the dude stepping off the tall ladder and fell to the earth, and then he finally put a backpack on him, which I don't think you can do, and inserted himself into orbit? Okay. Well, here's one for you. Actually, every object that you're trying to leave, in this case the Earth, has a sweet velocity called the escape velocity. Every object has what we call its own escape velocity. So when you hit that escape velocity or higher, you're going to be able to leave the gravitational influence of the object you're trying to leave. This is important. I kind of wanted to introduce you to this because we're going to talk about the escape velocity if you're on a black hole. Okay, and of course, you're not leaving. Okay, you can't go fast enough to leave a black hole. All right, last topic. So, I don't know, I've never lived where there are tides, but maybe some of you have. I think it's an amazing sort of thing. But the tides, of course, we're talking oceans, okay? Basically, the moon kind of lifts the ocean towards it because of gravity. Oh my gosh, really? Yes. Okay, the moon's gravity pulls hard on the side that's next to the Earth, and it actually makes a bulge of water there. So here's a picture of how that works. The moon makes a bulge of water where it is. Actually makes a bulge of water kind of in advance of it. So what you're looking here is the Earth. You're looking down at the North Pole. Here's the North Pole. And so if the Earth is rotating counterclockwise, so in a little bit in advance of where the moon is, actually it's pulling the water towards it. Now the Earth continues to spin once, it takes 24 hours to go around one time. The moon's moving too, but it's a lot slower. So all intents and purposes, we'll just leave the moon where it is and let the Earth spin. So as the Earth spins, so then also that blob of high water spins and follows where the moon is. So I think that is so cool. So you get a high tide, if you're wherever the moon is, and you also get a high tide like on the back of where the moon is. Okay, so you get two high tides. So the way this works is it takes the Earth 24 hours to spin around once, but it only takes it 12 hours to get back to that other high tide, and 12 more hours here, and 12 more hours here. So about every 12 hours you get a high tide. That's so cool. And I've seen pictures of beaches where the tide is low, and you see all these shells and everything, and then where the tide is high. That's so cool. Road trip. I know. And actually, Newton, I was talking to my mom about this morning. She's like, that is so cool. And she understands tides. And I talked to my mom about science a lot. And she was like, I forgot, she said it was cool. And I told her, actually, Isaac Newton was able to understood all this. So one last thing about tides. We kind of have a couple of situations where the tides are a little bit different. So when the tides are especially strong, we call those spring tides. It's kind of like you spring up, spring tides. When they're especially strong because the sun also gets involved. So if the moon and the sun and the earth are in a straight line, and that occurs both at new moon and full moon, if they're all lined up, then it gets an extra pull. So those are spring tides. And then if the moon is at a right angle to the sun, and we get those at first quarter and third quarter, then we have kind of a diminished high tide. Those are called neap tides. Neap. So this chapter will be due on, oh darn, I forgot to give you chapter assignments. I will post them and send them to you. So this chapter is due Monday, but I'm gonna put them on Twitter, put them under doc sharing, and email them to you, okay?
Good.
Thanks. All right, have a great weekend.